Thank you. Okay, so yeah, I'm Alex. I'm the machine learning platform lead at Monzo. And yeah, as has just been said, I'm going to be talking to you all about how we're unifying feature engineering across both data and backend. Okay, so before I jump in, there's a couple of definitions that I want to kind of clear up. So when I refer to backend, this is our call bank, and this is mostly all written in Go. It's event-driven, and it's hosted within AWS. And when I reference data land, what I'm referencing here is where our data warehouse is housed. And it's mostly in Python and SQL, and that all lives within GCP. We're going to be talking a lot about features, so I also want to kind of go over our three definitions of the types of features that we have within Monzo. We have just-in-time features, and just-in-time features happen on the request. So you can imagine this could be the current transaction that's coming in, and maybe we're deriving some features from that. Then we have near real-time features, and these are features that are kind of over some slightly longer window, and they're usually low latency. So this could be something along the lines of the transactions in the last hour. And then finally, we have batch features. And these are features that are kind of computed offline and would often have a lot longer windows on those. So an example could be app interactions over the last week. So these are our three kind of core styles of features. OK, cool. So to try and frame this talk, I'm going to be talking about this fictional case, which an ML engineer has come along, and they want to try and create a new model that is going to try and predict if a new large purchase is fraudulent or not. And for this model, they've found that actually they only need two features for this. And the first feature is the count of outbound transactions over the last 6 hours. And then it's the max transaction amount over the last 14 days for a particular account. OK, so the challenge. We've come up with a problem space that we want to solve. ML engineers come along, they've defined these features, they've been experimenting a bunch, they've created a bunch of models. They have a candidate model that they want to put into production. So they take this model, they'll wrap it in an API so they can kind of expose that to the rest of the bank. They would have defined these features in SQL. The data source would have been our data warehouse. For us, it's BigQuery. And then there's always this question of, I have a model API, I have my model, I'm confident it's going to be better, but how do I get that same data available when I actually go into the kind of online mode? How that happens prior to our work at Monzo was you'd have to call in a backend engineering team. That backend engineering team would look at those feature definitions that you've created. They would look at the SQL, they look at the data sources, and then they would try and translate that to a backend service. So they would rewrite that in Go. They would have to try and find similar data sources within backend to try and gather those values. They would go ahead and create one of these backend aggregators, and they're relatively simple, but they kind of look at data within Monzo, calculate those features, and then that will be served by some backend service to kind of mediate between these aggregators, and ultimately serve the data to your model. So what are the problems with this? We have multiple definitions for the same feature. So when you're backfilling your data, or when you're training your model, you're going to be having that written either in Python or in SQL. And then obviously when you transition to online, it's going to be written in Go. And not only is the language you're using different, the data sources under the hood are different. This could potentially cause a bunch of inconsistencies with those two worlds. And there could be slight tweaks in the definitions between the two worlds. There could be a misunderstanding of what that feature should mean. The data sources just could be slightly different, and then actually the feature online is very different to actually when you created that offline. There's also a high cognitive load. Like, this is across multiple teams. This is across multiple different styles of data sources. It's across multiple different languages. So in order to really get an answer of like how is this particular feature created, it can be quite tricky. And as well, it's coupling those two squads. So if you have an ML engineering team with a model, at Monzo, you can own the kind of life cycle of that model up until you kind of get it into that API. But prior to this, you had to then have that engineering team to come in and get that data available to you. So the ML platform team, we decided we wanted to solve this problem. This was causing a lot of friction when trying to go to production, and we set up with these 4 goals. The first one was we should have a single definition for machine learning features, and it should be optimized for the ML engineers. This is crucial because a lot of the kind of prior work that we have within Monzo was optimizing how can we make it easy for engineers to create features. The next thing is once you have those features created and you have a model and you're happy with this, it should be super simple to actually then transition that to online. So we should be able to take those same values that you use at train time and have them available in the core bank. Thirdly, we wanted a high level of consistency between those offline and online worlds. Ideally we'd have perfect consistency, but at very least we should be able to measure that. So when there is a kind of mismatch in that consistency, we can alert on that and address that. And finally, the ML engineers should be able to own the whole thing end to end, right? So they should be able to go from experimentation to evaluation to then actually going out and serving that and owning those features. Okay, cool. So how do we go about solving this? The first thing we needed to do is we have these two worlds. We have backend and we have data. We needed to have a concrete schema of a particular data, like a point of data, available in both environments. As I alluded to, Monzo is like event-driven, so most interactions with the bank have an event that's fired off. And every single one of those events is also logged out to our data warehouse. So we're building on this assumption that we have our atomic unit, which is an event. So we have the kind of historical events within our data warehouse, and then we have that same event in backend, and that's within Kafka in our world. So with that in mind, this is kind of roughly what one of those events might look like. This is obviously quite a slimmed down version, but you can imagine this is a transaction event, has an ID, account, an amount, and importantly, the timestamp at which that transaction happened. Okay, so going back to that example I said earlier, which was we want to try and detect if a new large purchase was fraudulent or not. And we had those two features. We had the feature which was I need to remember now, the transactions over the last 6 hours, and then the max transaction over the last 14 days. So this is how you would go ahead and define it in our new framework. We call this, we call it the feature transformation framework. It's not very catchy. It's really long-winded, but it kind of says what it does on the tin. So first of all, you would define a source. And the source here describes the event, and it describes the schema for that event. And you can see we have a name, we have the kind of the JSON path of how to pick that value off, and the type of that. And then you create a source. So this is a way of an ML engineer describing to us, I want this is what an event looks like, and when you perform calculations on it, this is how you access those properties. Next, you actually want to then go ahead and define the features themselves. So we've got two kind of features that we're defining here, and there's three core concepts here. There's aggregations, there's operations, and then there's windows. So given that those events that we've described in the source, we're going to perform two aggregations here. So the first one is looking at the amount, and we're going to get the count. I mean, it could have been ID, to be fair, this one, but we're going to get the count of transactions over a 6-hour window. And the second aggregation here is, again, very similar to the other one, which is I'm going to take the amount, and I want to get the max amount over the last 14 days. Then you specify an entity key. This is, for us, this will be the account ID. And then you kind of group all that together in an aptly named group by. So you've given us a source, and you've told us how to create those features. The next thing you want to do is you will then want to backfill those features, right? So we want to be able to create a training set that you can start training a model on. This is when the kind of this concept of a join comes in. So for our case, this fictional case that we have, we're looking at large transactions. So what we need to be able to do is we need ML engineers to describe to us what is the trigger event that you want to calculate these features for. So in this case, we define a new source, and that source here is for the event name is large transactions. Give a bit of a schema about that. And then what we're saying here is, okay, so in order to perform a backfill, I want you to take the left hand of that, which is the large transaction events, and then I want you to perform the group bys on those transactions. So to kind of help visualize that, because I know this is quite a dense representation of that you can imagine this is roughly what those tables look like. So on the left-hand side, there was the large transaction event. So here, this is a large transaction for account 132. And then on the outbound transaction events, these are all of the transactions for that particular user. And then ultimately, we'll take these two things, along with the definition of how to transform those values, and produce a table that looks like what we have at the bottom, which in this case is the large transaction ID and the two features that we defined, which is like the count of transactions in the last 6 hours and the max transactions in the last 14 days. Then we could also then join on the label to that, and this ultimately forms your training table. But one thing which is crucially important, we give you guarantees of a point-in-time correctness. So when you're looking at the large transaction, we'll make sure to only take in events that within the window that you specified. Just to go into that a bit more detail about point-in-time correctness. So imagine you're serving a model, and this point here on the yellow line is now, right? So I have a model that's in production, and a large transaction comes in, and I want to make a prediction about that. For the feature that we've been using, we would look over the last 6 hours of transactions, we'd count those, and then anything that falls out of that 6-hour window, we would disregard, right? So when we go to backfill a feature, we actually have more data than that, right? Because we're going to have the data that happened after that point, right? So it's super important that when we calculate these features, so when you give us that right-hand side, which is the large transactions, we make sure that when we actually calculate these features, we're not using anything from the future or outside of the window, right? And this is to avoid the kind of classic data leakage problem, which is the idea where you'll train a model offline, metrics look amazing, you'll then transition to online, and because it can't see in the future, you end up with a model that is just like awful, right? So we give you those guarantees. So as long as, and that's why it's super important you give us the like timestamp column. Okay, so I've given you like a relatively simple example of how to define features, but our system allows you to kind of chain features together, so you can have not just a single feature, you can have a feature that kind of goes off of and then joins to other events in the system, that then you can have like second order features. You could also use data from outside of the events table. So again, if you had like a slow moving dimensional table that you wanted to join an event on, we can kind of make that available. We can also join on like the just-in-time features. So say if there was a feature that was generated at the time of prediction that there isn't an event for, when backfilling that data, we can kind of join that in as well. And then finally, again, you saw a relatively like limited number of aggregations that you can do, but ultimately all of this runs on top of Spark. So we expose Spark SQL directly. So if you did want to do any sort of more complex aggregations on there, you can kind of interact with that. Okay, cool. So you've defined a source, you've defined a transform, and you've backfilled some data, and you've trained a model. And now you want to go online. So within our system, there's two types of accuracy. There is snapshot accuracy, and there's temporal accuracy. So snapshot accuracy is that we will calculate your feature values at midnight every day. And it will be looking back from that point backwards. So this is a great use case for something where it's like slightly longer windows. So our 14-day feature here, this would be a great use case for snapshot. Because we don't really care too much about the change that's happened in the current day. And then we also support temporal features. And these are point-in-time correct when actually serving these. So we try and give you the most up-to-date representation of that feature. So from the request that's on the side, which is again the yellow line, for batch, for snapshot, we'll be looking back from midnight and we'll have a value at midnight. But for the temporal, we'll be looking at the kind of most recent data that we have. Okay, so how do we actually deploy one of these temporal features? So temporal would mean that we have to have some way of processing events, right? Because we need to give you the most up-to-date representation of that particular feature. So we have events that come into the back end, and we have a relatively generic kind of event shipper service that basically takes those events and pumps them into our feature transformation framework. So when you deploy this feature, there's two things that get deployed. There's a streaming job, so this is Spark streaming, and again, if you remember, this is now in the core bank, so we're in AWS. This is actually on EMR. And all that will do is it will take the events in, it will filter those events, so say if you had any filters on them, so like maybe it was only inbound transactions you cared about, and it will do some light processing to those values, so they can be easily looked up in the key value store. So events come in from the event shipper, we light processing and filtering, and then they get dumped within our key value store. And then we will then push the definition of that feature to a service called the feature fetcher. And what that does is it will take the definition of the feature, and then when someone requests that feature, so say I want to see this feature set for account 123, we will look up at that definition, we will fetch the data that we require, and then we will perform the aggregation on that particular, for that particular entity. So one thing you might have noticed here is that when you're usually talking about stream processing or kind of processing events, you're often thinking about an event comes in and I want to perform an aggregation on that event. So for an example, maybe you're counting the number of transactions. What you could do is you could say every time an event comes in, I'm going to look at that, I'm going to do some aggregation on it, which will be count in this case, I'm going to increment the number, right? And we can kind of see the logic there. Whereas what we do is we do aggregation on read, which is we will store all of these events in a relatively raw format in our key value store. And at the point where you request the value, we will then go look up at those raw events and then apply the aggregation like on the hot path. So you can see here as a rough example, say if we had 3 events, when a user comes in, they'll say, okay, I want you to get me the inbound transactions for the last hour for account 123. And what we'll then do is we'll then look at the definition of that feature. In this case, it was like, for an hour. We'll calculate an hour backwards from the point you requested. And then we will only look up the feature values, the event values for that time range. We then have those, and then we'll calculate those. So why would we do that? So if you imagine the other world, which is doing these aggregations every single time an event comes in, you can imagine the complexity explodes, right? Because instead of having to calculate for a single, for this case, like a single large transaction, we would be having to calculate these values for every single transaction that came in. So we're ballooning the amount of computation that we have to do. We're ballooning the amount of like values that we have to store, because whereas this is just like at the point of a prediction, we can then calculate the values, and you have like the most up-to-date version of that. Some other kind of slight meta points that we can do here is we can also include like the current transaction that's happened on the request. So we can also like merge in these just-in-time features, which is quite complex in a kind of traditional streaming world. But there's obviously a cost to this, which is we're actually doing the aggregation on the hot path of that transaction, or that prediction. But typically we've been seeing like very small amount of overhead and latency added for that, somewhere between kind of 10 milliseconds up to sort of 50 milliseconds, which is well within our tolerance. So for us right now, this makes a lot of sense. Okay, so for snapshot deployments, these are much simpler. Probably should have started with a simpler one first, but you can imagine here, this is the snapshot feature is a feature that we calculate at midnight every night. So here, all we do is we have a batch Spark job that will read the values from our data warehouse, calculate those aggregations, and then ultimately fire those values to the online store. We'll then also, again, very similarly to what we did with the temporal, we'll also push the definition of that feature to the feature fetcher. And then finally, the feature fetcher does very little here, because all of the aggregation is actually done offline, right? So we perform those values offline. So this is great because you can have like very long windows, and we can store that very densely, because there's only like one entity per row, because you have that value and it lasts that whole day. But again, you are sacrificing the fact that you will not get new data until the following day. Okay, so one of the big goals we had was to also monitor online and offline consistency, right? So one of the big problems we had was the fact that because of these definitions change, or maybe the underlying data changes, so we needed a way of like objectively monitoring, okay, how different is the data online versus offline? So as I mentioned, we have this definition of the feature, right? So what this means, and we've used that to create those training data sets, and we've used that same definition to create those features online. So what we do is whenever you kind of request a value from, and we calculate those values online, we will then log that value to our data warehouse. And then what we'll do is we'll use that as the right bound of the table, and we'll recalculate those features. And then what we do is we then just do some relatively simple kind of consistency checks. So we do equality checks to see if there's anything missing or mismatching. You'll also have like the classic kind of numeric test to see has a distribution of a feature changed from online to offline. But you can imagine there's a lot of data that potentially could go through here, and the computation and cost of doing this for every single feature that we had could be quite high. So again, we do like relatively heavy sampling on these features, on the values that come back. So it's a trade-off of cost versus like actually getting consistent values. Okay, cool. So this system, we've called it the feature transformation framework, but it's actually based on this tool that is open source called Chronon. This is a tool that's been developed by Airbnb and Stripe. It's an incredible tool. I'd highly recommend you go and check it out. It sets up a lot of these kind of paradigms that we spoke about. It sets the foundations for those. So yeah, great tool, really good like kind of open community where there's a lot of people kind of posting about that. So definitely go join in on this. It's pretty hot right now. Okay, cool. So that's the system. We allow you to define your features once. We can then create them offline, and then we can, as a platform, give you as close to guarantees that the values will be correct online as possible, and when they're not, we can alert on those. But what were some of the learnings of this? So that sounds great on paper. You've just solved all feature engineering. We never need to think about inconsistencies. But actually, there were some kind of quite sticky points. The first one is we have tens, if not hundreds of thousands of types of events that happen at Monzo. And the definition of these events is pretty tricky to nail down. So even just trying to understand like what transaction event should I use to calculate a particular feature is not an obvious question to ask, not an obvious answer. There's a bunch of work that's going on internally to kind of improve this, because this is like a Monzo thing that we need to kind of improve on. But again, we're going to kind of hopefully try and, that was like a sticking point, which was like, what event should I use? The second is we're now reasoning with events versus like existing data models. So prior to this, you'd have all your data warehouse, you'd have lots of like models that run on top of that data that kind of clean the data, aggregate it in a nice way, and then you would have created features off of that. The problem there is that those aggregations they don't happen within backend. So we can't use those same data sources. So where an ML engineer typically would have gone to like our transactions table, instead they now have to think about the raw event. So what is the raw transaction event and apply those transforms to it. So again, there's this like, you're changing the kind of level at which the data you're kind of rationalizing over. And finally, so although I said we're using like an open source tool here, you can imagine like this is cross-cloud, like cross-department. It's a huge project. And actually just integrating this tooling and kind of building the Monzo abstractions around it took a lot longer than we expected. And it was definitely like a lot of learnings to take, and it was very complex. But yeah, the future, right? So we're relatively early on in this journey, right? So this is something that is like a new thing at Monzo. This isn't like the default way to create features, but it is going to be like this is the way that we're going to kind of solve this issue. So one thing that we've noticed is that the interface that you saw that we defined, which is like kind of class-based, where you have a class, you put in properties, you kind of in a way try and like merge something that looks like SQL but sounds like SQL but doesn't look anything like SQL. So we've been experimenting with like different types of interfaces that we could have on top of this. So one of the kind of more popular ones we're looking into at the moment is like a pandas style interface. So from a data scientist point of view, it just looks like they're writing pandas. They're just defining group bys and aggregations in the same way, but under the hood, we're handling the computation of that in batch and Spark, and then we'll also handle that same thing in streaming. Event discoverability, I've already said that. This is something we really need to make better. We have like really like all of our events within Monzo are kind of defined by proto. So in theory, we have like a programmatic way where you can see what events are and what the types of those events are, what properties are on there. And we want to do some more integration there. Thirdly, like feature metadata, other than the definition of the feature and how to transform it, where it came from, there's no description about it, right? So when you define these things currently, it's kind of like hopeful that you talk to the person who defined that feature to be able to give you more explanation. So we kind of really need to tighten up that. Fourth, we're doing a lot of like LLM style applications. This sits perfectly within that domain. So although I've very much spoken about this in the kind of traditional sense, LLM style workloads still need data and it still needs to be point in time correct. You still need to be able to kind of evaluate these systems in the same classical way that you would with machine learning, and then you still need to make sure that data is the same when you go on serving, right? So it fits very nicely into that. And then, yeah, the goal is this becomes the default way to do all feature engineering across Monzo. All right, that's my talk. We're hiring, and if you want to follow me, there's LinkedIn.